Good afternoon, everyone. We're going to go ahead and get started. My name is Kimberly Sukalas with the Lister Hill Center for Health Policy, and I'm very excited to welcome all of you to today's webinar with Dr. Jeffrey Shaman. And now it is my absolute honor to introduce our speaker for today. Dr. Shaman is the professor in the Department of Environmental Health Sciences and the director of the Climate Health Program at the Columbia University Mailman School of Public Health. He's the faculty chair of the Earth Institute at Columbia University and the senior associate dean for faculty affairs at the Columbia Climate School. He studies the survival, transmission, and ecology of infectious agents, including the effects of meteorological and hydrological conditions on these processes. His work to date is primarily focused on mosquito-borne and respiratory pathogens. He uses mathematical and statistical models to describe, understand, and forecast the transmission dynamics of these disease systems and to investigate the broader effects of climate and weather on human health. Dr. Shaman holds a BA in biology from the University of Pennsylvania and an MA, a Master's of Philosophy, and a PhD in climate and geophysics from Columbia. And with that, Dr. Shaman, I will let you get started.
Thank you so much, Kimberly. It is a pleasure to be here. And I'm going to just dive right into my talk. I'm going to be talking today a bit about some of the work my group has done on infectious diseases, trying to understand the linkages with climate and meteorological variability, as well as some of the underlying processes and how that has led us to a lot of the modeling and forecasting work that we've done, and how we've then applied that to the COVID-19 pandemic. So I'm going to just acknowledge funders up front, because if I don't do it up front, I tend to forget to get to the slide at the end, and also acknowledge a whole wealth of collaborators whose work you'll see here. Some of them are going to be featured more than others. In particular, Dr. Senpei, who's now an assistant professor at Columbia University. Some of his work will be featured prominently as well. So I'm going to start by talking about influenza rather than COVID right now, and talk about how it relates to atmospheric conditions. And to do so, we need to understand a few things about its epidemiology and modes of transmission. So what you're looking at here is a 31-year climatology, if you will. It's a daily averaged excess pneumonia and influenza mortality. So excess pneumonia and influenza mortality is considered a pretty good proxy for influenza infections. And what you're seeing here is a 31-year climatology. So each day represents an average for all January 1s, 1972 to 2002, all January 2s, et cetera, through the whole of the 365 days of the year. It's shown for California and New York State. And what you can see in this smiley face of sorts is something that all of us who have lived in temperate parts of the world for any length of time, particularly pre-COVID-19, really intuitively know. And that is that flu is something that occurs in the wintertime. It's a wintertime malady. It has a seasonality to it. And we have this pronounced wave that very often takes place in the wintertime that stresses hospital resources, produces a lot of excess mortality, and causes a lot of morbidity of a milder variety, keeping people home from school and work. Now, this seasonality of flu has been noted for a very long time, maybe 2,500 years. People have noticed that there's certain types of conditions that people would get in temperate parts of the world during the winter time. Obviously, this is well before germ theory, but there was an understanding that there was something going on that seemed to be making people sick. Now, people have tried to explain this seasonality for a long time. And I would say that the hypotheses that try to explain why flu is seasonal fall into three broad categories. The first has to do with changes in people's contact pattern and mixing patterns. Here, the idea is that when it is colder outside, people will spend more time indoors. It tends to coincide with the school session as well, outside the growing season. So the kids are indoors as well. And that proximity, that person-to-person closeness in a sealed environment comparatively, where the air is recirculated and has less opportunities to mix freely with the broader environment, allows for the transmission of the virus from person to person, and hence we see a spike in influenza in the wintertime facilitated by that proximity and increased contact. The second of the hypotheses has to do with changes in our immune function. And here the argument is that our immune system is sensitive to vitamin D levels, melatonin levels, and these are sensitive to sunlight in and of itself. Sunlight exposure, solar insolation exposure foments the production of melatonin and vitamin D within the body system, which enhances our immune function. And so it's possible, conversely, during the wintertime, that people's immune systems are less primed, such that they may be more susceptible to infection, or additionally, once they are infected, they may be less equipped to fight it off. So they may run higher viral titers, shed more of the virus, and be more contagious. And these processes feedback on themselves such that in the wintertime, you're getting more infections, the average person is more contagious, and the virus spreads more efficiently. Hence, you see the wintertime surge of cases and deaths due to influenza. Now, the third rationale has to do with environmental conditions. And there, the environmental conditions are fed by changes in temperature and humidity and maybe solar insolation. I should add that for the previous one, obviously in the wintertime, the sun's at a lower angle in the sky and day length is shorter, so there is less melatonin and vitamin D production. But for this third category, it really has to do with the idea that maybe there's some change in the atmospheric conditions that's actually influencing the virus once it is expelled from the host. So when a person is infected with flu, they shed the virus, much like we do with SARS-CoV-2. It's shed out in droplets and aerosols into the external environment, and it's subject to ambient conditions in some way that may modulate the survival and the transmissibility of the pathogen. Now, I should add that for flu, as for most, in fact, all respiratory viruses, we're not really certain of how it is transmitted. We know how it can be, but we don't actually know how it predominantly is. There are understood to be 4 modes of transmission. Some people will define 3 and group 2 of them here. Some people even define 2 and group 2 of them into sets of 2. But for our purposes here, I'm going to just look at all 4 modes. And so the modes of transmission represent the possible ways that flu gets from one infectious host to a susceptible host. The first is direct transmission. So if I'm sick with the flu and I am running a high viral titer, I'm shedding the virus in my oral and nasal mucosa, I come home, I kiss my wife, I can give it to her. That's direct contact. The second mode is indirect contact, and you'll see it says fomites underneath it, and fomites are any object upon which droplets containing virus may settle. And here the idea is that if I'm sitting in front of my computer right now and I'm giving a talk to you, while I'm breathing and speaking, if I'm singing or coughing or sneezing as well, I'm going to be shedding droplets and aerosols out. Some of them are going to land on the computer keyboard. If somebody else were to come along and use this keyboard, they're going to pick some of them up on their fingers. They can go off and eat a cheeseburger or rub their eyes or something of that sort, and they can then transfer the virus into their system and become infected that way. So that indirect route, which uses this intermediary, which is the fomite, is another means by which flu might be transmitted. The third is called droplet, and that has to do with the fact that some people may be close enough to a person that when they're speaking or singing or coughing or sneezing and they release droplets, some of those droplets actually may just catch a person in the face. The same way we heard about there's this 6 feet of distance you want to stay apart during the early periods of the pandemic. That was very much focused on this idea that maybe it's about 6 feet where you're mostly in the clear from any droplets that somebody could spew out in a sneeze, which is the most violent exhalation. The last mode is airborne, and this has to do with aerosolization. And what you can see on the right is a photograph of a sneeze, and you can see that the goop is coming out of the mouth, not the nose. And in the sneeze, there are droplets of various sizes. You can see that some of them are rather large and already settling out at the bottom of the photo, but there are a lot of it that's actually quite small. And the smaller stuff there is small enough that it's not going to immediately settle out. As a matter of fact, it could even desiccate somewhat or partially down and remain aloft on the turbulence in the air for a very long period of time. And that aerosolization causes us to have airborne particles that may have viable virus in it that people, of course, because we're breathing, can inhale into their upper or even lower respiratory tract and set up an infection. Now, flu was discovered in 1933, I believe it was identified. That's when the virus was first formally identified. People have been studying the modes of transmission and its survival really since the late 1930s to try to understand it. And I would say from 1940 to 1975, a lot of the consensus, I would say, was that flu is transmitted in an airborne fashion by aerosols. Then you went in, I would say, from 75 to 95, there was a lot of discussion of fomites and their role and an emphasis on washing hands. though the evidence that washing hands really limits respiratory diseases like the flu is limited. It's very good for diarrheal diseases, so please continue washing your hands, but its effectiveness at curtailing the spread of acute respiratory infections is less clear. And then I would say, in the late 90s, it switched back to airborne. I've seen a lot of disagreement about it and what's the real driving force behind it. I think there's a lot of dogma and narrative about this. And we saw this during the pandemic, in particular, early on, with people making declarations that it was transmitted by a droplet, and nobody had ever even done an experiment with this virus yet. So there's a lot that we don't know here, and it's very important for controlling viruses such as this. Now, this leads me to talk to you about something a little more specific. Those were some generalities about flu, its seasonality, modes of transmission. I'm going to talk about a guinea pig experiment that was run at Mount Sinai Hospital here in New York City by some virologists. They had discovered that guinea pigs were actually a very good animal model for studying the transmission of type A influenza. And they set up a chamber experiment. And in the chamber experiment, they would take 8 guinea pigs and they would infect 4 of them with type A influenza. They'd put the guinea pigs on 4 levels, one exposed, one of the susceptibles, and one of the ones that have been infected on each level. They were in separate cages, and they put them in a chamber with an airflow that was going from the infected towards the exposed at a light level. And they put them in those chambers for 72 hours, and they repeated the experiment 20 times at different fixed temperature and relative humidity conditions. So in other words, each time they did it, they held a different combination of temperature and relative humidity conditions in the chamber for 72 hours. They then looked at the end of it all to see, well, how many of those exposed guinea pigs, 0, 1, 2, 3, or 4, had actually become infected with influenza. And what they found is that there were differences depending on the environmental conditions, and that they were seeing more of the guinea pigs that had been exposed become infected while in that chamber at colder temperatures and lower relative humidity conditions. Now, I read this article and I was immediately thinking, well, why are they looking at relative humidity? Relative humidity is an interesting variable. It's very meaningful for many systems, including many biological systems. But I knew if they're playing around with both the relative humidity and the temperature, they're not actually getting a measure of how much water vapor is in the air, only how close you are to forming fog or a cloud. So that's what relative humidity is. It's a measure of how close the environment is to start forming fog or a cloud. It's represented by this equation on the right, which says that relative humidity equals the vapor pressure of the air, which is a pressure-based measure of the actual water vapor content of the air, divided by the saturation vapor pressure, which is the point at which rates of condensation and evaporation are equivalent. It's when a cloud would begin to form in the air. Now, the thing is that E sub S, that saturation vapor pressure, varies highly, very strongly as a function of temperature. And that has a consequence because it means that if the temperature conditions change, and they were changing the temperatures in their chambers, the amount of water vapor needed to hit 100% relative humidity differed based on temperature. So I looked at this and I said, well, it's good that they looked at relative humidity, but why didn't they also look at absolute humidity? Why didn't they look at some mass or pressure-based measure of the amount of water vapor in the air so they could see whether it's really sensitive to how close you are to saturation or to the amount of water in the air? Now, again, why explore relative humidity is actually seen really well in this graphic on the right here. The blue line on the right shows temperature on the x-axis in degrees Celsius and vapor pressure, this pressure-based measure of the amount of water vapor in the air, on the y-axis. The blue line is 100% relative humidity. It's something called the Clausius-Clapeyron equation. And what it shows is that as the temperature rises, going from 0 to 40 degrees Celsius here, the amount of water vapor needed to begin forming a cloud increases exponentially. And the line below it is the 50% relative humidity line. And what it shows with those 2 X's on that green line is that the air at 50% relative humidity and 25 degrees Celsius has almost 4 times as much water vapor as the air at 50% relative humidity and 5 degrees Celsius. And these are very real world conditions that you experience going from winter to summer in many parts of the US, for instance. So I read this and I knew all this stuff about the thermodynamics of water vapor in our atmosphere. And I said, well, why not? Why didn't they look at absolute humidity? So what I did is I said, well, they got the data in their paper. I can take the Clausius-Clapeyron equation, which is that first equation there. I can take that equation for relative humidity there, which is the second equation, and I can back out a measure of the vapor pressure in the chambers that they ran and see if there's some sort of greater association with vapor pressure and the number of guinea pigs that became infected at the end of 72 hours. So I repeated their analysis and I found it using regression, the same sort of marginally statistically significant relationships where at colder temperatures and lower relative humidities, there was a greater chance of percentage of guinea pigs that became infected at the end. It says percent transmission, but it's really fraction. That's 0 to 100% you're seeing there. And it really represents 0, 1, 2, 3, or 4 guinea pigs becoming infected. And you can see as you go from low relative humidity to high, the number or the fraction of guinea pigs that were infected decreases. Same as you go from cold to warm in temperature in degrees Kelvin. And then when you go to the bottom one, it shows you vapor pressure. And vapor pressure is measured in millibars. And you can see that as you go from low vapor pressure to high, the number of guinea pigs that were becoming infected in those chambers dropped as well. And it was more statistically significant. So looked at this and said, all right, well, that's interesting. What else can we say? What else can we do about this? Well, what we saw is that the authors of this paper had posited two hypotheses for why there was this sensitivity to relative humidity. And we wanted to think about both of them. The first was that virus-laden aerosols, which are called droplet nuclei, are more efficiently produced at lower humidity levels due to the increased evaporation of expelled particles such that more virus remains airborne longer. Well, what does that mean? That means that when you sneeze or cough, or in the case of guinea pigs, which don't sneeze or cough, when you breathe or chatter, you're excelling a distribution of droplet sizes, just as we saw in that image of the sneeze from that first slide I showed you. And some of those are going to be very, very large and settle out. Some are going to be very small and remain aerosolized, but there's going to be some in an intermediary range that are going to start to evaporate in the subsaturation air. And if they evaporate enough, they could get small enough before hitting the ground that they could become aerosolized as well. So their argument was, well, maybe what's happening is that when it gets to be drier, more of the goop that comes out of the guinea pig's mouth in these droplets and aerosols is remaining airborne because more of it evaporates down to small enough size to be aerosolized, and therefore there's a larger infectious load floating about in the chamber. And I should note that the guinea pigs aren't able to touch each other and they don't cough or sneeze, so we're really talking about aerosol or airborne transmission in this experiment. So what I said is, all right, well, that's all well and good. Let's make a little model out of this using some of the microphysical processes at play. We'll have something that represents the velocity of settling of a droplet and another that represents its evaporation. And that's what those two equations show. We're then going to take it and we're going to model that evaporation and sedimentation, those competing rates at different temperature and humidity levels, except we're going to use absolute humidity. And we're going to see how long it takes the droplet to hit the ground, or if the droplet gets small enough that we consider it aerosolized, a droplet nuclei. And that's what you're seeing in the upper right there. And it's showing you what happens and how long in color it takes for the droplet to hit the ground. And what you could see is as conditions get drier, as you move down, and warmer as you move to the right, it's taking more time, for the droplet to hit the ground because it's getting smaller and smaller, and so it's not falling as quickly because of drag forces that are acting upon it. And then it gets small enough in some instances at very dry and warm conditions in the lower right where it says DN to become aerosolized. The stuff on the upper left, that's unrealistic conditions that are supersaturated that we don't really experience in our atmosphere, so we ignored that. So we looked at that and said, well, this doesn't add up because it's saying warmer and drier, not colder and drier conditions is important. So then we looked at the model that we built and we said, well, look, if evaporation is really the driver of what's going on here, then really we should be able to see it from how quickly evaporation rates proceed. And that doesn't go as a function of temperature or relative humidity or absolute humidity, vapor pressure. It goes as a function of this funny thing that has the 1 next to it, which is the vapor pressure deficit, E minus E sub S divided by T. So we said, if that's really what's driving it, that's what should pop out as the strongest relationship in that experimental data. So we did the same kind of regression with that we had done before with temperature, relative humidity, and vapor pressure. And you see that on the lower right. And what we can see is that there's no relationship at all. So that suggests that it's actually not evaporative dynamics that's driving the transmission process. However, they had a second hypothesis. And the second hypothesis was that for some reason, the virus inside the aerosols survives longer. It remains viable. It doesn't break apart or degrade or get prematurely activated when conditions are drier. Now, it turns out that there had been a lot of studies dating all the way back to the early 1940s that had looked at influenza virus survival in response to relative humidity and temperature conditions. Some of them used an apparatus such as what's shown on the bottom left there. It's called a Goldberg drum, where you atomize or aerosolize the virus in aerosol droplets, and you put it in this rotating drum that has fixed temperature or relative humidity conditions or both, and then you can sample it to see how long the virus remained viable over time. It's a lengthy process because you have to then measure the amount of virus that's there, which is usually done by plaque assay. So it's not easy to do, but there are a number of studies over the years that have examined this. However, none of the studies at the time had looked at absolute humidity. So I went combing back through the literature and I looked to see if there were any studies that had actually met two criteria, where they'd looked at the viability of the virus as a function of both relative humidity and temperature, and they had printed the data in the paper, because I needed the data and both those characteristics, temperature and relative humidity, to back out the absolute humidity as I did before. I found one paper that had that. It was a 1961 study by Harper, where he had used a Goldberg drum, just as I told you. And what you can see is a similar analysis, except this time, instead of for transmission among guinea pigs, it is actually what percentage of the virus remained viable at 1 hour, 6 hours, and 23 hours after atomization into the Goldberg apparatus. What you see is that when you look at the top plot, you can see that as you get to more humid relative humidity conditions, you're seeing less of the virus remaining viable. As you get to warmer temperature conditions in degrees Celsius, you're seeing less of the virus remaining viable. And then when you get to the bottom one, where we backed out vapor pressure, you're seeing actually a very, very clean nonlinear relationship. As a matter of fact, if you look at the lower right plot, if you take a log regression of 1 hour viability of influenza virus as a function of vapor pressure conditions, 90% of the variance is explained by this single factor, absolute humidity. So we saw this and we said, well, that's very interesting. All right. And we then looked around and we said, we have this relationship where at drier absolute humidity conditions, the virus remains viable longer and it's more transmissible among guinea pigs. Well, what are the conditions in wintertime? Well, if you look at the conditions in wintertime represented indoors and outdoors on the plots there, for conditions in the northern hemisphere, for the outdoors and indoors from Scandinavian measurements, you can see with the blue line for vapor pressure that vapor pressure, a measure of the amount of water vapor in the air, is minimal in wintertime. And that's consistent with the relationship that we saw. So that seemed to us a smoking gun. It seemed to indicate maybe there's this very strong sensitivity to humidity conditions. And in particular, we're talking about the absolute humidity conditions, which are both phased correctly indoors and outdoors to produce this kind of outcome, where you're going to have the virus viable longer once expelled from a host, and therefore more transmissible to people in the vicinity of the person who's contagious. So we looked at this and we said to ourselves, well, I wonder if we could predict individual outbreaks. You know, that would be a very interesting phenomenology. We had been able to set up a model of influenza where we took observed humidity conditions and used it to force a simple susceptible infectious recovered model, one of these compartmental models of infectious diseases, and we could actually replicate the seasonality of influenza throughout the United States. And that was really kind of cool. We could also see that anomalous excursions of low humidity in October, November, December were associated with, in the following weeks, the onset of the flu season. So we began to see a lot of empirical evidence that this was seen at epidemiological scales, and we could actually model the seasonal cycle of flu using observed humidity conditions. However, the question we wanted to then ask was, well, can we use that to predict specific outcomes? can we actually predict what's going to happen over the next 4, 8, 12 weeks in terms of the burden of influenza, how many cases there are going to be, what kind of impact it's going to have on hospitals, et cetera. And so what we did is we tried to do that with our mathematical model forced with humidity conditions. And we found that it doesn't work. And the reason it doesn't work is because even within the simplest model describing the dynamics, the transmission dynamics of influenza, an SIR model, you're getting irregular nonlinear dynamics. And this can also be seen from observations of flu. If you look at the right here, this is a different proxy. This is just influenza-like illness for New York City estimated there. You can ignore the yellow line because that's actually the 2009 pandemic second wave. But the other lines are all seasonal flu outbreaks. And you can see that it's actually inconsistent when flu takes place. The timing of it, the overall magnitude of the peak, the duration of the outbreak, and the total area under the curve is highly variable from year to year. This is what we would like to predict, but because it's nonlinear and irregular, it's actually difficult to predict systems like that, unlike a linear model. However, there are systems where the dynamics are nonlinear and irregular, for which they have been able to make accurate, skillful, reliable predictions. And the most obvious example is weather forecast. This too is a system, as I said, that is nonlinear. As a matter of fact, deterministic chaos was pulled out of it. It's irregular, yet at time scales within the limits of predictability for this system, depending on its nonlinearity, we are able to make skillful forecasts that have a multitude of uses within society today. So we said to ourselves, well, what are they doing in weather prediction? And could we take that and apply it to infectious disease prediction, in this instance, prediction of the flu? So we said to ourselves, what is it that they do? Well, we need to mimic the strategies they have. And in numerical weather predictions are based off of 3 principal ingredients. The first is you need a model, a numerical model that can describe the dynamics of the system. For weather, that's a model that describes the dynamics, the thermodynamics, and the radiative transfer processes of the atmosphere. For us, it's going to be something like an SIR model. We're going to start really simply and see if we can do it. As a matter of fact, we're going to use that humidity-driven SIR model that I just described for you. The second thing that you need in order to make this system predictable is you actually need observations of the system. And for weather, they get it from everywhere. They get satellites, ground-based stations, ocean buoys, ships, planes, balloon soundings. They're picking up information on temperature, wind speed, rainfall, humidity, pressure, etc. And they're using that information to inform the models. For us, it's going to be information on, well, how many cases of flu are there? What is the ILI rate right now? And the third thing you need in order to make this system work are things called data assimilation methods. And what these are used to do, and I'll explain this in a moment, is to rigorously combine the observations with the model in order to inform the model of conditions as they are right now, in order to make a more informed, more accurate, reliable forecast. So again, our model is going to be a humidity-forced SIR model. This is a simple compartmental model where we divide a population into 3 groups: those who are susceptible to flu, those who are currently infected with the flu, and those who have recovered from the flu and are not susceptible. They can have another S, they can actually return back to that compartment again, and that's what that ADA parameter is showing you in that schematic up above. Now, the rates of transition between the compartments are guided by these various Greek letters, which are determining how quickly people move from one compartment to another. And one of the key things is that moving from S to I is a nonlinear process. And that it makes it act kind of like a damp pendulum, if you will, in the presence of humidity forcing. So that's the first ingredient we have. The second ingredient are those observations I talked about. And the one that we focus on is something we call influenza ILI plus, influenza illness plus, which is taking influenza illness, which is a syndromic surveillance of a fraction of people visiting sentinel clinics who are presenting with ILI, which is defined as a fever of 100 degrees Fahrenheit or greater and a cough or sore throat. The fraction of people presenting with that multiplied by, among those people actually tested for flu that week, how many tested positive. So if we multiply those two together, what we actually do is we filter out all the other respiratory elements that actually can also cause ILI symptoms. So we use this as our measure of flu. The third ingredient are these data assimilation methods. And as I said, The idea is to actually ingest or assimilate the observations of the system from the real world into the model so that you can adjust or fit the model so that it can simulate what's happening thus far. Now, there are all sorts of forms of them. They go by all sorts of names like particle filtering, Kalman filtering, variational methods. They're used in many disciplines, including numerical weather prediction, where they're used to optimize a state space system, which is what that SIR model is. So why do we do that? Well, the reason we do this is because the model is very prone to error because of its nonlinear dynamic. There are errors in the model structure, but there are also errors in the model parameters that we might put in there and in the initial model state that we have. And if we get those wrong, those will amplify over time because the model is nonlinear and the system is nonlinear. Left to its own devices, if the black line is the true outcome, the model might simulate something like this. To put it more in an epidemiological framework, if this is a time series of influenza-like illness or ILI plus, and those numbers on the x-axis are weeks, the true outcome might be the thing in black, and that red might be what your model simulates or forecasts if you don't inform it about what's going on. That kind of prediction that you're seeing in red is really quite bad. It's awful, right? And it's particularly awful if you initiated it in the 15th week, because at week 15, you can see there's already been 6 or 7 weeks of rising cases, and it will be good if the model knew about it. You use the data assimilation to assimilate those observations, bring them into the model, inform it so that the model can find a solution of its parameters and state variables that actually are best aligned with what's going on in reality. So that's the name of the game. The name of the game when you use these data assimilation methods, which are a form of Bayesian inference, is to take real-time observations and use those data assimilation methods to recursively adjust and optimize the mathematical model. It is an inference problem. We're estimating unobserved state variables, such as what fraction of the population is susceptible, and parameters, such as what's the contact rate, what's the basic reproductive number, what's the infectious period. None of those things are observed, but we're inferring it on the fly by combining this Bayesian inference algorithm with our mathematical model. And the idea is that if the data are rich enough for a given system, the state variables and parameters should be identifiable. We should be able to find them. And by simulating the past up to the present, the system has a higher probability of forecasting the future. Now, all this is done in an ensemble of simulations rather than one, which allows us to understand the uncertainty of our forecasts and our estimates. And we actually run the ensemble into the future to generate a prediction. So I'm just going to cut to the chase and show you what it looks like when it works. This is a forecast that we did in real time in the 2012-2013 season, almost 10 years ago at this point. So it's for Salt Lake City, Utah, week 50, which is the middle of December. The black X's show you observations of ILI plus that we had in hand. The red X's are observations that we did not have in hand at that time because it was the future back then. The blue line is the mean posterior, and the gray lines are the means of ensemble forecasts, 150 of them. Each line is a 200-member ensemble mean. And what you can see is that there's some things that it does very well. It captures the overall area under the curve, it captures the duration of the outbreak and the descent, and it captures the timing, when the peak will occur, week 3 of 2013. And this is all 5 weeks in advance of when it actually occurred. Now, not only do we want to be able to make a prediction like this, we would like to know in real time how good that prediction is. We don't simply want to say, well, flu's going to peak in 5 weeks. We'd like to say there's a 90% chance that flu will peak in 5 weeks, or a 20% chance that flu will peak in 5 weeks. And you notice this is very analogous to what you hear in a weather forecast. There's a 70% chance of rain tomorrow, or a 30% chance of rain tomorrow. We want to be able to deliver those kind of calibrated certainties associated with our forecasts. And it turns out we can do that if we look within the ensembles that are generating these mean forecasts you see here. So if I take one of these gray lines here and I split it apart, you get to see what the 200-member ensemble looks like. And it looks like this, a lot of spaghetti. And you can see the magenta line shows you the mean there, that mean trajectory, which was represented by one of those gray lines last time. And what you can see is that it spans actually the whole observation space, which is really important statistically. But more importantly, what we could also see was that as the disagreement among those ensemble members diminishes, as they come into tighter agreement, you're actually more likely to be making an accurate forecast. So when they're closer together, it might be a 70% chance that flu will peak in 5 weeks. When there's more disagreement, more variance, then it might be that there's only a 10% chance that flu will peak in 5 weeks. So this discovery was really interesting because it allowed us to start thinking about calibration and probabilistic use of the forecasts and thinking about how reliable they were, which is a formal forecast metric. In that initial run we first did real-time forecasts in the 2012-13 season. There were a number of issues we wanted to verify. How accurate were the forecasts relative to just historical expectance? Is the expected accuracy, those probabilities I just told you about, are they reasonable? And how far in the future can we make a prediction? We know for weather, it's kind of limited because the atmosphere is very nonlinear. This system isn't as nonlinear. Maybe we can predict farther into the future. What we could see, and this plot shows you here, is that we were able to make much more accurate forecasts with this model Bayesian Inference data assimilation framework, which is the SIRS EAKF thing in the blue line there. It's showing you the fraction of all forecasts for 108 cities that were accurate by week. So week 50, again, is the middle of December, and you can see by week 52, the last week of December, 63% of the cities were being accurately forecast. 84% of them actually peaked 2 or more weeks after week 52. So this is in advance of when they were peaked. We were able to say when the peak was occurring. The smears in the bottom show you what you get just from historical expectance, and it doesn't do nearly as well. We also looked at the lead times, and we could see that in instances we could predict as far ahead as 12 weeks in the future. But as you went farther and farther into the future, the accuracy dropped off. The likelihood you're going to get a good prediction was off. But that reliable predictions, decent predictions, could certainly be made 4, 5, 6 weeks in the future with this system. Now, since we did this first work, we've been doing a lot of work on forecasts in the last decade. We've been trying to build more reliable forecast models of different forms. We've been trying to improve the data assimilation, optimization. We've been trying to figure out how to interpret them and work with public health agencies for use. And we've been looking at other disease systems as well. So here's some examples of some of the stuff that we've done. We built a web portal for delivering real-time forecasts of the flu, which has actually, because of the pandemic, been quiescent for the last 2.5 years. We've also, built more complex models. This is a metapopulation model using data from 35 states for flu that showed that we could actually make more accurate predictions if we had data from multiple locations linked together, allowing people to travel and move from one place to another. We also were able to transfer it to systems like West Nile virus and develop forecasting systems for those systems. And we also used it to develop projections for the West African Ebola outbreak in 2014. Now, I want to switch gears just a little bit here to talk about inference for inference sake. If you remember what I said here, in order to make the forecast, we're using those data assimilation methods to infer the conditions of the model, kind of like aiming a cannon before firing it to make forecasts. We wanted to know what's the basic reproductive number, what's the contact rate, what's the latency period, what's the infectious period, how many people are susceptible. And that inference that you make in order to set up a forecast right now is also very important in its own sake. It's the analytics that you want to know about a disease system. And we've actually used that in many forms. We used it to look at the spread of Ebola in Sierra Leone and try to understand how it moved from place to place. We used it to study the transmission of methicillin-resistant Staphylococcus aureus in hospital settings among patients using a very detailed network agent-based model. But I'm now going to actually jump to COVID for the last 10 minutes or so and tell you a little bit about what we used it for there. We had done a project just before the pandemic. It ran from October 2016 to April 2018, roughly, called the Virome of Manhattan. It had a number of branches, but one of them was a cohort we established of about 200 individuals who were parents and their kids, toddlers in daycare centers and some of their siblings, teachers and students at a high school in northern Manhattan, people who worked at the Columbia University Medical Center in the ED, nurses, doctors, orderlies, et cetera, and people who worked at Columbia University's Medical Center as well more broadly. What we asked all these individuals to do is to join this cohort and then on a daily basis, tell us their symptoms associated with respiratory infection. So every day they would tell us on a Likert scale of none, mild, moderate, or severe, how they felt vis-a-vis cough, sore throat, body aches, a runny nose, sneezing. And they just enter it into their phone and go directly into a database that tracked those individuals when they signed in. In addition, they'd also tell us if they had stayed home from work or school, if they'd taken medicine, or if they'd gone to see a doctor because of their respiratory symptoms. And then once a week, regardless of how they felt, we swabbed these individuals. And we would take that back to the lab and test it for 18 different viruses, common respiratory viruses. Now, remember, this is pre-COVID. There are 4 coronaviruses, things like OC43 and NL63 that infect humans commonly. They cause mild illness. In this table, we've lumped all the types of viruses together. So influenza type A and B are all lumped, RSV A and B is lumped, different numbers of parainfluenza, et cetera, et cetera. And you're seeing for those 7 different groups of viruses there, the number of episodes that we documented. These are infectious episodes where an individual was positive for the same virus for 1 or more weeks in a row while allowing a 1-week gap to account for false negatives or temporary low shedding. And you can see we got 32 episodes of flu, 30 episodes of RSV, 275 of human rhinovirus, et cetera. If you look at the next column that says MA, that means medically attended. That means that the person reported that they went to see a doctor because of how they felt, because of their symptoms. If you go to the next column, it shows you the probability of seeking medical attention given an infection with that virus. It's just the MA column divided by the episode column. And you can see for all of them, the numbers are less than 0.25. They're less than a quarter. Even for something as severe as flu, less a quarter of people who got the flu went to see a doctor. Now, the way that we conduct surveillance for respiratory viruses is passively. We wait for people to seek clinical care, and if they do so, they can get slapped with that ILI label or tested for a virus. As a result of it being passive, most infections are undocumented. Now, remember, we're detecting these as shedding. Many of them are contagious for a period of time. We're just capturing them at one period of time. But if you look at them, all of them are, the majority of infections are undocumented. And so what did this tell us? It told us that the reason these common respiratory viruses are common is because most people don't know they have them, and they don't slow down. They don't stay home from work or school. In other words, they do what you or I used to do before the pandemic when we had a little sore throat or sniffle in the wintertime, which is nothing. You'd still go to work, you'd still go to school, you'd still go shopping, you still go out to the movies or dinner. If you had a business trip or vacation, you get on an airplane and you go. And the reality is, in doing that, we were transporting our viruses around. We were taking them to new establishments, new locations, new geographies, and we were inserting them into those populations there. We were unwittingly spreading them. So in January of 2020, when we saw what was going on in China and the epicenter in Wuhan, and we saw how quickly cases were fanning out throughout China and spreading to all these other cities, and then hopping on airplanes and going to Thailand and South Korea and Japan and the US, we immediately said to ourselves, this virus is behaving like a common respiratory virus. There has to be a lot of people who don't know they're sick, but they're contagious. They know they're not unaware that they're infected, but they're spreading the virus. They're either shedding it pre-symptomatically, asymptomatically, or polysymptomatically, but they're spreading it and they're going about their normal activities like they're not sick. So what we did is we built a model to actually quantify this. Remember that inference I'm talking about here? We want to estimate what fraction of infections are undocumented and how contagious are those undocumented infections. So what we did is we built a metapopulation model that describes the transmission dynamics of SARS-CoV-2 in 375 cities and links them using travel records from location-based services off of people's cell phones in China. We coupled this model with data assimilation methods and used the observations, daily observations from all 375 cities during a 14-day period, January 10th to 23rd. Now, we used that limited period because this was prior to the lockdown that was imposed in Wuhan on January 23rd and very rapidly spread to the majority of China. And what we're trying to do in this model is separately represent documented and undocumented infections and see also how their contagiousness varies. I don't have too much time, so I'm gonna rush ahead a little bit, but one of the important things that we did here was to show that the system was identifiable, that using the observations that we had in hand, that we would be able to make the estimates of those critical parameters. And the two parameters I'm interested in are the middle two on the left one, mu, which is the relative contagiousness of an undocumented infection compared to a documented infection, which is a reported case, and alpha, what fraction of infections are reported cases. So we showed that the system was identifiable, and then we actually applied it to the real data. And the results are shown in this table here. Again, I want you to focus on alpha, the reporting rate, and mu, the relative transmission rate. You can see that alpha is estimated to be 0.14, which means that we're estimating that 14% of the infections in China during that 14-day period prior to the lockdown in Wuhan were actually documented. That means 86%, the vast majority, are undocumented. Further, it indicates that mu is about 0.55, which means that per person, on average, undocumented infections are roughly half as contagious as documented infections. So what did this mean? Well, it meant that there might be a lot of spread going on from these undocumented infections. Now, one of the other things that I don't show here is we were also able to see that there was a lot of pre-symptomatic shedding of virus as well. Now, we were able to take those estimates of those parameters, plug it back into that stochastic metapopulation model, and reconstitute the outbreak, which meant that the fit was actually very good in free simulation. But we then could say to ourselves, okay, well, this is a model. We can do a little counterfactual simulation here. What if we shut off mu? What if we say, let's run it again, but let's turn off the ability of those undocumented infections to spread the virus? So we take mu from 0.55 and we set it to 0. And the red is the free simulations you saw on the previous page. And the blue shows you 100 different free simulations with mu set to 0. And you can see that there's an enormous reduction in daily cases at the national level, in Wuhan city, and the number of cities that had 10 or more cases reported over this 14-day period. What we see is that there's an 80% reduction in the total number of cases as a result of shutting off the undocumented infections. So what did this mean to us? Well, it suggested to us that this virus was not going to be contained. It unfortunately has an epidemiological property that it shares with common respiratory viruses, in that a majority of the people who are infected are not documented. They're not aware that they have the virus when they're contagious, or at least portions of their time when they're contagious, and they're going to be able to spread it very readily without some extremely draconian measures to stop that. And if we look at this compared to the other coronaviruses that we know of that have infected humans, the first is SARS-1. This didn't have any subclinical infections. There were no undocumented infections. We've seen that from serological studies that haven't found any. For MERS, the Middle Eastern Respiratory Syndrome, that had actually a low respiratory rate. There was some mild or asymptomatic cases, not a lot, but it also wasn't that transmissible. The seasonal coronaviruses, which go by those alphanumerics right there, those produce mild infections. And a lot of them are mild and they get around really easily, but they don't have that fat tail where they were causing a lot of mortality, particularly in the elderly. So we saw this and we said to ourselves from these analytics, this is a problem. We have a novel respiratory virus to which the world is completely susceptible. It is capable of spreading from people who have no idea they're infected and may never actually manifest symptoms. And it is not killing everybody, but it's going to infect enough people and put enough people in the hospital that it's going to cause substantial health disruption and substantial mortality. Now, I was going to tell you a little bit about the seasonality of the whole thing and some other stuff, applications to the US and such, but I know I'm running a little bit long here, so I will stop and take your questions now. Thank you so much.
We have had quite a few come in during the presentation. I'm going to start off by asking, someone said, when you're creating your modeling data, do you offer this as a service to state and local health departments, or do you look at outcomes on more of a national level?
We built this model out at the county scale for the United States for all 3,142 counties in the US. We built a metapopulation model in mid-March and began running simulations and projections and using it for analysis along the way. We did the exact same thing for the US. And the table that I didn't show there, matter of fact, why don't I just share my screen and show it very briefly? It'll make it a little clearer. So the table that I didn't show right here is, this is the analysis with that metapopulation model for the US. And you can see here, alpha is even lower. It's 8% rather than 14%, which was consistent with the fact that we didn't have a lot of testing capacity in the US because of some errors and bungles that went on at the time. And the relative transmission rate was a little higher. We've been using it for all sorts of simulations. So here's an example of an estimation of some of the epidemiological characteristics over the course of 2020, shown nationally for metropolitan areas, and in the maps it's shown on a county by county basis. This shows you the susceptibility at 2 points in time here. This is August 1st and this is December 1st, 2020. What fraction of the population had actually been infected at that point? We've also been using it to generate projections, and we post these on a GitHub repository. We've contributed them to the CDC and other groups as well, and we've done this for the last 2+ years since March 2020.
You actually answered both of the other questions that we have in the Q&A, but I just saw one in the chat. Stephen's asking, can the flu model control for the percent of the population that have been vaccinated for the flu? How to control for how well the flu shot anticipated the right formula?
The latter issue, no. But for the former issue, there are a couple ways that we can do it. We can try to explicitly put in vaccination rates, but that can be a little bit tricky. It's one way of doing it. The other is that you treat it as an estimation problem. When you're doing the data assimilation and you're assimilating cases, the model has to find a solution that represents what's happened thus far and provide a good estimate of susceptibility in the population. That susceptibility reflects prior history of infection and vaccination. And so the vaccination is subsumed into that estimation. People who got a vaccine for which it was effective will manifest in how quickly the virus moves through the population, and it's going to change the estimation of the susceptibility. So there's an implicit way of doing it that relies on those data assimilation methods that doesn't disentangle resistance because of natural infection from resistance from vaccination, but it does include the vaccination effect.
Very good. So we do have another question from Dean Irwin, and he says, what are the implications for the impact of climate change on seasonal flu transmission, given your findings related to humidity and temperature?
I think that's a great question. My sense is that if we look at how flu seasonal patterns manifest right now, once you get outside the tropics, literally north of the Tropic of Cancer, south of the Tropic of Capricorn, you get a strong seasonality where it's a wintertime malady. When you move equatorward of the tropics, it starts to become twice a year. And then when you get to the deep tropics, there's no seasonality at all. It happens at any time. It's highly irregular. I think as conditions warm, it depends on where you are and where you're connected. Florida, South Florida, is still a little bit north of the Tropics of Cancer, but it has potentially the possibility of moving into some sort of more irregular pattern, but it's also very phase locked with what goes on with the rest of the US because there's so much commerce and interaction there. So, things in Chicago and New York are making it so that we have a strong wintertime signal still for flu that may affect Florida. The other thing is, though, if you look at Toronto, and you say, well, in a warming world in 100 years, Toronto's climate's going to be like Atlanta. Well, Atlanta right now has a strong seasonal cycle of flu. It doesn't affect it so much as cause a phase locking so that it's a wintertime malady, not a summertime malady. So I suspect for a lot of places, it will stay phase locked where it's a wintertime malady. But for some places, maybe Florida, maybe a few areas in like Mexico or other places, it might move more times like into something like what we see in the tropics. It might become more regular.
So the last question that we had, this was asked pretty early on, and they were asking if other diseases other than influenza were modeled. And I'm going to turn that around a little bit because you mentioned Ebola and a few other diseases that you've worked on. Are there any viruses where this modeling doesn't work, that you found that the modeling isn't as effective?
The modeling, look, in practice, the modeling can be effective for any pathogen, provided you had enough understanding of what's going on with its transmission dynamics and the observations are rich enough. So the limits are places, viruses, locations where there's a paucity of data. It's going to be very difficult to do this kind of data-driven modeling that's informed well. And so the ability to actually apply these model inference systems that combine a mathematical model and data assimilation methods is going to be limited where you do not have good data. That can make it very challenging. It's, if you have good data, you can learn about it. You can even use the modeling to learn about the transmission dynamics and pick it up. So usually the data is the limiting reagent. I will also say, though, that for the purposes of forecasting, it's also important that the data is available in real time. So, for West Nile virus, I showed it to you and I said, I showed you very quickly a plot and said, we've applied it to West Nile virus. We showed that you can actually make good forecasts of West Nile virus if you have estimates of human deaths from it and mosquito pool infection rates. The problem is those data aren't available in real time. And particularly problematic are the human cases. They're released at a lag of anywhere from 2 to 12 weeks. And if you're getting the data 12 weeks after it took place, it's too late to really conduct a real-time forecast for a system like this. So it's not only the richness of the data, but it's the availability in real time that is important as well for operational forecasting. You can still use it retrospectively for the analytics, though, to try to understand what went on and to understand if could you forecast the system if you had it in real time.
Well, thank you so much. Before we sign off, if people want to follow your work a little bit more, either with your lab or your personal work, where can people get in touch with you? Do you have a website? Do you have any kind of social media that people can follow you on?
I actually finally got on Twitter in October 2021, very, very late to the game. But I've noticed that I just don't have an inclination to tweet a lot. So I wouldn't bother there too much. But I do have a website. If you just go and Google me at Columbia University, you'll find the website there and you can see what we're doing and our publications and activities and such.
Well, perfect. Thank you so much for your time. I know that this was a wonderful webinar, one of our most attended that we've had this year. So we really appreciate your time. And again, thank you so much.
My pleasure. Take care, everybody.